Welcome everyone, I'm Christopher Teruna, a PhD student at the Acoustics Research Group in the Delft University of Technology. So thank you for being here today. Now I'm currently being inside the anechoic chamber, and right next to me is a vertical wind tunnel where we can perform various sort of aeroacoustics experiments where we can study different kinds of sources of noise with various applications. And in my personal study, we have been looking at the noise produced by turbomachinery, such as modern aircraft turbofans. Some of you may have already noticed that this kind of engine produces a very loud tones, this whistling kind of noise, and also a loud level of broadband noise, something that sounds like a rushing wind. So the first thing that we need to address is how can we have something that mimics the noise produced by a turbofan inside a laboratory setting. Some of you might immediately think about, what if we bring a full turbofan set inside the wind tunnel? Of course, it would be quite complicated in order to do so. So instead, we start to work with simpler model. And in this case, what we have here currently is what we refer to as the rod linear cascade model. Now, what we are trying to achieve here is to model what we refer to as the rotor-stator interaction noise inside a turbofan. This process is generated by the interaction between the turbulent fan wake, as the fan spins inside the engine, with a set of non-rotating blades that we refer to as the stators. This interaction process will result in a very loud noise being produced. So again, inside this test section, we are also going to do the same thing. We have the set of blades over there, 7 in total, which represents the stator inside the turbofan. And to replicate the fan wake, instead of using a spinning or rotating set of plates, we use one single cylinder. So the cylinder will then produce this periodic vortex shedding that we refer to as the common vortex thread, and the periodic impingement of this common vortex thread onto the cascade is what will produce the noise. So now we have something that has similar noise characteristics as the one of the turbofan, and then we can do the study in this laboratory. On my side here is the rod linear cascade test section that I've been telling you before. What I'm holding here is the rod itself, or the cylinder. You can see how slender it is, and we are going to insert this rod into the slot that's available here at the side of the test section. And when now the rod is inside of the flow, inside of this test section, then we'll start to produce this common vortex shedding, and then the wake will then interact with these 7 sets of plates inside the test section also, which will produce a very loud noise. We are going to perform 2 main measurements here. The first one is, of course, the noise measurement. And in doing so, we are actually using a total of 8 microphones that's mounted on this circular arc that we're going to place around here at the back of the test section. And with these different microphone placements, we can measure how the noise is being heard from different positions around the test section itself. And in doing so, we will be able to tell what we refer to as the noise directivity pattern. Depending on the type of acoustic measurements that we are doing, the microphones may have to be placed differently. And behind me, you can see these are 2 examples how the microphones can be placed differently depending on the types of acoustic data that you would like to obtain. The first one is what we refer to as the beamforming measurement. With beamforming, we can try to localize the source of noise inside our models. So in this example, to my left, you can see there's a grid here. Microphones can be placed at certain distances from each other along this grid. And when the microphone is configured in a certain way, we would be able to combine the data recorded by each microphone in order to produce an acoustic source map. And the second kind of measurements that we often do is what I've mentioned before, that is the noise directivity measurement. With that, we can tell what is the preferred sound radiation direction from the source to the listener. And for that purpose, we've been using this acoustic arc, where then the microphones can be placed at the different angles relative to the direction where the source is located at. So microphones at different angles should be perceiving a different level of noise, and with that we can try to determine what is the noise directivity pattern of a certain particular source. Now the next part, of course, is to perform the flow measurements, and in this particular setup that you can see here, it's a setup to measure the flow that is being produced from within of this test section. So on top of the test section, we've installed this wake rate. And on this wake rate, there are multiple total pitot pressure probe and also a few of these static pressure probes. And what they measure is what is the total pressure and static pressure inside this flow field. And from there, we can apply a bit of Bernoulli equation to try to find out what is the velocity at the outlet of this test section. Now, looking closer to the test section itself, you can see that there's this solid plate here that's covering the 7 plates that's being installed there. And you can see on each plate, there are this zigzag kind of structure. Those are what we refer to as the tripping strips. We apply it there to enforce turbulent transition on the plate itself. Otherwise, we are going to receive this annoying tone that is not what we would like to measure. And yeah, below this test section itself, we have let's say a special contraction that we have been using to produce a relatively high-speed flow. And in this particular case, we apply let's say a free stream flow field of up to 65 meters per second inside of this test section. And the outlet velocity here is expected to be around 90 meters per second. So that's around 300 kilometers per hour or so.